Hello and welcome to the second lecture of week 10 of the course Introduction to General Relativity. In this lecture, we will work out the Schwarzschild solution, which is the first ever non-trivial exact solution written down for the fully nonlinear Einstein field equation, no approximations, and represents the gravitational field or space-time metric outside a spherical distribution of matter energy. As for references for this lecture, I will cite the following two sources. The first is Carroll's lecture notes on general relativity, which is available for free on the archive. This is the archive number, chapter 7, and these pages. And the second one is Ohanian and Rufini's textbook. I'm using edition 3, chapter 7, and this section. Okay, these pages. Apart from that, as per usual practice, lecture notes for this lecture will be posted on the NPTEL-NOC website. So let's look at what's on the agenda for today. Today, I'm going to discuss vacuum solutions of GR. And by GR, I mean no approximation, no linearization, fully nonlinear GR. And we will see that those vacuum solutions turn out to have a critical property that those metrics have vanishing Ricci tensor, that is, they're Ricci-flat. Okay, so Ricci-flatness is a characteristic property of vacuum solutions. And then we will discuss spherical symmetry. What do we mean by that in differential geometry language? And then what are the implications for the metric? And consistent with spherical symmetry, we'll write down an ansatz for the metric, space-time metric. And then we will plug that spherical symmetric metric ansatz into the Ricci-flatness condition, because we are looking for solutions which are vacuum solutions, that is outside of sources, T mu is 0. And with some help from the Newtonian limit, we will be able to write down the Schwarzschild solution. All right, without further ado, let's begin the lecture. So the Schwarzschild solution, as I said, apart from being the first ever non-trivial solution written down for the fully nonlinear field equations, physically it is very important because it represents the gravitational field, or the space-time metric, produced by a spherically symmetric mass distribution, okay, for a spherical symmetric. As a result, it describes a variety of physical situations, astrophysical situations. For example, the gravitational field produced by any non-rotating or slowly rotating star or planet or other more exotic astrophysical objects such as white dwarfs and black holes. And so long as they're rotating very slowly, so that rotation is not a big deal, and they're spherically symmetric, the solution to the Einstein equation, or better yet, the gravitational field or space-time metric produced by such objects, will be of the Schwarzschild solution form. As I was mentioning, the Schwarzschild metric is an exact solution, not an approximate solution to the full nonlinear vacuum Einstein field equation. Contrast that with gravitational waves, which we covered in the last couple of lectures. Gravitational waves is a solution only to the linearized Einstein field equation, and hence it is not as non-trivial as the Schwarzschild solution. Einstein field equations are fully non-linear, and they're extremely difficult to solve. So this is why this is a bit of a miracle that Schwarzschild was able to write down the solution within a month of Einstein publishing his paper giving the field equation. So we will study how to obtain the solution mostly in this lecture. And in the next lecture, we will be interested in what is the resultant modification to Newtonian/Keplerian trajectories of matter and light under this field produced by the spherical object. That is, we will look at time-like and light-like geodesics in the Schwarzschild geometry. This solution, we will quickly try to study how to obtain this solution. All right. So the first thing I made was that the vacuum solutions of general relativity represent Ricci-flat metrics. So let me first define what we mean by vacuum solutions. Where in this case we are interested in the metric outside of a spherical distribution, mass distribution, because we are outside the mass distribution. The T mu at that point in the field is 0. So in the field equation, whenever we set T equal to 0, T mu equal to 0, we call that solution a vacuum solution. Okay, solutions for which T mu is 0, but there is no source. Actually, it is incorrect to say there is no source. We just mean outside source. Of course, there must be a source to produce a non-trivial gravitational field, but this equation holds whenever we are outside the source. Okay, so this is the Einstein field equation with the 8 pi g Newton over c to the 4th T mu term set to 0, the right hand side set to 0. And in this case, what you can observe is if I contract both sides by the inverse metric inverse g mu, this term, the first term will give me r, and the second term will give me this half times the metric contracted with the inverse metric with both indices contracted. That will give me a factor of d, the space-time dimension, and then this r remains as it is. So we have this equal to 0, and so long as d is not equal to 2, this implies that the Ricci scalar must vanish. Ricci scalar must vanish. Okay. All right. So this equation, the Einstein vacuum Einstein field equation, when we contract with the inverse metric, it shows that the Ricci scalar is 0. So taking trace, Ricci scalar is 0. And then if I plug back r equal to 0 in the left hand side of the Einstein field equation in vacuum, what we get is that r mu nu must be 0. That is the Ricci, not only the Ricci scalar, but the Ricci tensor itself must vanish. Okay? So this is a general result which tells you that whenever I set T mu to 0, that is vacuum solutions of GR are always going to be Ricci-flat metrics. That is metrics, Ricci-flat metrics are those for which the Ricci tensor vanishes. Now, that the Ricci-Riemann tensor is also vanishing. That is, Ricci-flat metrics are not necessarily Riemann-flat. The converse is true. If you start with something which has Riemann tensor vanishing, Riemann curvature vanishing, of course, Ricci is given by the trace pieces of the Riemann tensor. So if the Riemann vanishes, Ricci will definitely vanish. But Ricci vanishing, that is the trace of the Riemann tensor vanishing, doesn't mean the all components of the Riemann tensor vanishes. Okay, so they're interesting things to study. If a spacetime is Riemann flat, that is the Riemann curvature vanishes, that means there is no gravitational field, no tidal forces, so no gravitational field at all, and Riemann flat just means Minkowski spacetime. Okay, so when we say flat spacetime, we mean Riemann flat spacetime, which is same as Minkowski spacetime. Okay, however, vacuum solutions are not Riemann flat necessarily. In fact, they are Ricci flat, and this Ricci flat represents non-trivial gravitational field. Gravitational fields are there. Okay, so we are interested in solving this equation. So the vacuum Einstein field equation, we can just solve for the Ricci flat equation, that is Ricci tensor vanishing. But before that, as I mentioned, that we are strictly interested in the case when we have a spherical distribution of matter energy. So remember, typically what happens in other branches of physics, for example, electromagnetism. There also you solve for a spherical electric field outside the sphere or a point object, point charge. Both the situations are spherically symmetric. And while solving for the electric potential outside the sources, in such cases, in electromagnetism or electrostatics is a better situation, what we do is we choose a coordinate system which has that symmetry, right? Spherical symmetry. So we will convert to spherical polar coordinate system and then work out the solution. For example, you can use Gauss law or some other solution to work out. So the first, you choose a coordinate system which is best suited for the problem, and then solve for the potential in that coordinate system. In this case, the Laplace equation, because we're solving for outside sources. So Laplace equation is the correct equation, which is Laplacian of phi vanishing. So first we write the Laplacian in spherical polar coordinates and then try to solve it. Okay. General relativity is different from that, because in general relativity, the coordinate system, that is the metric with the metric coefficient, is the coordinates along with the metric coefficients in that coordinate system get determined as a part of the solution. So remember, when we are solving for the metric, we are determining the coordinate system along with the metric coefficients in that coordinate system. Okay, so we have to solve two problems at once. This is completely unlike in any other branch of physics, where you're free to choose a coordinate system at your will that is unrelated to the variable you're solving. For example, the electric potential which you're solving, choice of the coordinate system is unrelated. In case of general relativity, you determine the coordinate system and the metric coefficients which represent the various gravitational potentials in that coordinate system together. Okay, they go hand in hand. So we will set d equals 4 because we're interested in 4-dimensional spacetime. We can repeat this analysis for general dimensions. I will not do that in the lecture, but in the lecture notes, I have a small section in which you can generalize whatever we are discussing today for d equals 4 to arbitrary d, general d. It's completely straightforward. There's not much difference between d equals 4 and arbitrary d. Okay, but just for simplicity, I will just do the case for d equals 4. Okay, on the lecture. So d equals 4 means we have 4 coordinates, labeling each spacetime point. And let me call those coordinates x0, x1, x2, and x3, with x0 being time-like. That is, the g00 component would be negative. Okay? And similarly, g11 would be positive, g22 will be positive, g33 would be positive, so that we have 3 space and 1 time. Now, we have to determine the metric coefficients in this coordinate system. So g mu x as a function of these. So first question is, what does spherical symmetry even mean in such an abstract setting? It's not that I can choose a spherical coordinate system, spherical polar coordinate system, because the coordinate system is to be determined as a part of the solution itself. So what, in such an abstract setting, what does spherical symmetry even mean? Okay, and here, to answer this, we will refer to the concept of Killing vectors, which we use to define isometries or symmetries of the metric. Definition of spherical symmetry is this, in the language of GR isometries. Out of those, a subset of Killing vectors should have the symmetry, could be the symmetry group of the sphere. Okay, should contain, so the isometry should contain, so the Killing vectors, the isometry, set of isometries form a group, which is called the isometry group, right? Most of you, I hope, are familiar with the idea of a group. And symmetries in physics turn out to be elements of group. Symmetric transformations are elements of group. So this isometry group, which is the elements of symmetries of the, whose elements are the symmetric transformations of the metric, which leave the metric invariant, should contain at least one subgroup, which is SO3, which is the symmetry of the sphere. Most of you know this from your study of classical mechanics and of quantum mechanics. This SO3 group is known to most of you. It represents the symmetric transformation which maps the sphere back to itself. Okay, so now we have a working definition of what a spherical symmetry means. Means I'm looking for a spacetime metric which must contain a set of Killing vectors which are the same as the symmetry group of SO3. And let me just elaborate what do I mean by that. So SO3 means those 3 Killing vectors, K1, K2, K3, there'll be 3 of them. This satisfies the algebra of SO3. Okay, so this is the SO3 algebra, or some people know it as the SU2 algebra. SU2 is the universal cover of SO3, but locally these two groups look the same. So locally SO3 is same as SU2, and most of you can remember this SU2 algebra from your classes in quantum mechanics or even classical mechanics. Okay, this is what I mean. I'm looking for a metric, spacetime metric, which has a set of at least 3 Killing vectors, and 3 Killing vectors which satisfy this SU2 algebra. Then I will declare that metric to be spherical symmetry. So this is a working definition of a spherical symmetry in GR. Now, the next point, I won't go much into the mathematical details, but I will put a result in differential geometry, which is known as Frobenius theorem, which says that if your spacetime has spherical symmetry, that is, there are 3 Killing vectors which obey the SU2 algebra, then the manifold, by which we mean space-time, can be foliated into two-dimensional sheets parameterized by 2 coordinates such that the metric on those sheets is same as S2. So let me define what I mean is that if there exists such Killing vectors which obey the SO3 algebra, then the manifold will look like such concentric surfaces, a collection of concentric. The space-time, you can think of each point there is there is a spherical surface, and you can draw a dot at each point, passing through each point, and the whole manifold can be foliated, that is represented in terms of sheet. For example, in Minkowski space, most of you know, can be thought of as a collection of infinite number of surfaces, flat surfaces stacked up. At each point there is a flat surface, so it can be foliated in sheets which are flat. On the other hand, something which is spherical symmetry, Frobenius theorem says that it can be foliated into spheres. Okay, so the metric on these foils or foliations or sheets is the same as that of S2, which is the two-dimensional sphere, up to some overall scale. Okay, so, and because it's a two-dimensional surface, it will be parameterized by 2 coordinates, which I will take to be x2 and x3. Okay, so the manifold looks something like this: x2 and x3. You need to vary to go around this spherical foliations. If you go around the foliations, x2 and x3 is changing. x1 and x2 are fixed. I'm sorry, x0 and x1 are fixed. And if you go from one foil to the other foil, keeping x2, x3 fixed, then x0 and x1 are changing. Okay, so in this direction, let's say I've joined points on different foliations or different foils. I'm joining points which have the same x2 and x3, and I draw some kind of a curve or surface through that. Then x0 and x1 are varying. Okay, as I jump from one foil to other foil at constant values of x2 and x3, the values of x0 and x1 are changing. Okay, so as a result of Frobenius theorem, we can see that these 4-dimensional space-time metric has can be foliated, that is thought of as a collection of foils, 2-dimensional foils, and in which, as you vary x0 and x1, you go from one foil to the other. Okay, so this is the derivation is I will skip it, but you can find in some advanced books, not in Carroll and Ohanian and Finney, but in some other books like Wold, you can find the derivation. But I feel the derivation is not particularly. So, as I said, that Frobenius theorem tells us that on the foil, the metric is that of a sphere. And sphere metric, which I'm representing by this d omega square, d omega 2. This 2 is for 2-dimensional sphere, and this omega square is because ds square. The metric gives you the squared info. Okay, so denominator, the downstairs 2 is for the dimension of the sphere, and upstairs 2 is because it's a squared metric. Metric is a squared interval. Okay, so this everybody I hope recognizes. This is the metric on the sphere. Now, what Frobenius theorem tells us that if I fix x0 and x1, and if I just vary x2 and x3, the metric on that foil is given by the sphere metric times some factor c, this prefactor c, up to our overall scaling. So that scale factor is c, which of course can depend on x0 and x1. Okay, that can depend as we go from foil to foil, that x0 and x1 can change. But as long as we are in one foil, it is going to be proportional to the metric of the sphere S2, two sphere. All right. Here x2 I was calling as theta, and x3 I'll call as phi because they parameterize the sphere. So it's natural to take the colatitude and the longitude. And x0 I will call t, and x1 I will call r. In terms of this, I can write the most general possible metric which I have written, which is not very pleasant to look at. So it has many terms. Some terms you can instantly recognize. Minus a times dt squared is the time part, and then dr squared, a term proportional to a mixed term, dr dt, And then of course there is our sphere part, and then we can have terms which are dt d theta, dt d phi, dr d theta, so on and so forth, and dr d phi. Okay, I think this phi got truncated, but there is a d phi here. D phi. Now you will notice that the metric coefficients are only functions of t and r and not theta and phi. Now that is understandable. If the metric coefficients become functions of theta and phi, we will not have spherical symmetry. Okay, we will especially those of you who remember how to construct Killing vectors. One way of spotting a Killing vector is that the coordinates should not appear in the metric coefficients. So if del theta and del phi are Killing vectors, then theta and phi better not appear, in particular del theta, not del phi. These will be independent of that, right? Sorry, phi. So these will be independent of that. Not necessarily true, but one way you can make sure that this is a Killing vector if you make the metric coefficients independent of theta and phi. Otherwise they will violate spherical symmetry. Okay, they will violate spherical symmetry. I think as a homework I had given already how to find the Killing vectors of the sphere. This you should be able to show there are 3 of them, and then if they are there, then you can show these coefficients a, b, d, e, f. They cannot be functions of theta and phi. They have to be only functions of t and r. Okay, so if the Killing vectors of the sphere are Killing vector of the full metric, space-time metric, then you cannot have any dependence on theta and phi, and you can only have the metric coefficients depending on t and r. All right. Now, the terms which are linear in theta and phi should also be ruled out by spherical symmetry, because they distinguish these terms which are linearly proportional to theta and phi. These terms distinguish between clockwise and anti-clockwise. Okay, they theta positive and d theta the same amount negative. So if I look at directions which are for a given theta, if I go d theta in the clockwise direction and d theta in the anti-clockwise direction, the metric would look different, and hence spherical symmetry will be ruined. So same thing for d phi as well. So these terms cannot be there, and we should just drop terms which are linear in theta and phi. So last 4 terms drop out, and we are just left with 4 terms. So E, F, G, H drop out, and we have a simpler looking, I won't say simple, but let me say simpler ansatz, in which you have 4 terms turned on, in which one of them is of course the sphere metric, nothing to determine here. This is already determined. All we have to do is to determine the undetermined coefficients are A, B, D, and C. Okay. Now, general relativity has this property of diffeomorphism invariance or general coordinate invariance. I'm free to choose whichever coordinate system I want to work on. So we will exploit this freedom of performing general coordinate transformations to switch to new coordinates by defining that the coefficient of the sphere part be given by new coordinate r tilde square. So I define r tilde to be equal to this, a function of t and r. Whatever function is undetermined, doesn't matter. I will call that to be my new coordinate squared, r squared. Okay. Of course, when you do this, you have to eliminate r from everywhere, right? Dr that you can do using the chain rule. Everywhere you find dr, you've got to substitute this from this equation. From this equation, you have to invert to write r in terms of r tilde and t, and then dr will be given by using the chain rule. Dr dt plus dr d tilde dr tilde del r tilde d of r tilde. Okay, you have to use this in everywhere, wherever you see dr, and substitute this. Okay, and you also anywhere there's r dependence, you have to invert this to write down r in terms of r tilde and t, and then substitute there. If you do all that, do all that, of course, these coefficients will all change, A, B, D, but whatever they are, they're still undetermined, and I will call them A tilde. And now they see their functions of T and R tilde, okay? T and R tilde. R has disappeared because I redefined, I used the general coordinate invariance, general coordinate transformation freedom to eliminate R in favor of R tilde. So R tilde comes in the sphere part. So this is not C anymore. This is R tilde, again determined. And then we are left to, so from 4 we are down to now 3. Okay, 3 coefficients. We haven't even solved it. We are just still using general coordinate symmetry to simplify the form of the metric, and it will turn out general coordinate transformation is enormously helpful because it allows us to basically simplify the metric unjust before we actually solve it. Now this piece, as I said, there are 3 coefficients. We can combine these terms by completing squares. So if I complete the squares, there'll be a term which is proportional to dr squared with some coefficient, some combination of these A tilde, B tilde, and D tildes, as well as this combination squared, this combination of dt minus something, some functions of t and r tilde times dr tilde whole squared. So we've completed squares and combined these 2 terms into 2 things. And again, I'm going to use my freedom to do coordinate transformations to define a new coordinate t tilde such that this is equal to t tilde times some integrating factor. Of course, I cannot, I cannot pretend that this is not needed. This is equal to 1 because integrability, we have rules in which whether this is an exact differential. This is not always an exact differential, but if you don't have an exact differential in 2 dimensions, you can always find an integrating factor. So f is the integrating factor, which can always be, you're guaranteed to find that in 2 dimensions. So using that integrating factor f multiplied by this differential, then this becomes an exact differential, and I can write it as d of something, d of t tilde in particular. So let's say I find that integrating factor. I found that because it is guaranteed to exist in 2 dimensions, at least for 2 variables, dt and dr, if you have that. Then I can write this even simpler. So now you can see I have something proportional to d tilde square plus some function, undetermined functions, times dr tilde square plus something which is entirely determined. And then of course A tilde, F, B tilde, D, these are all undetermined anyway. So I'm going to call this whole thing something and this ratio something and simplify the form. So we will relabel A and B, etc., and call this ratio to be A and this whole thing to be B. Doesn't make a difference because we haven't really solved anything. Just the form of an undetermined function. Okay. And then further simplification, we can get rid of the tildes. Anyway, we haven't determined the coordinate system. This is a generic coordinate system, what we call them. Whether we call them t tilde or t, doesn't matter. So I will relabel t tilde to be t. And I will relabel r tilde to r. Okay. If I do that, then this notation even simplifies further. This metric looks even simpler. So we have boiled it down to 2 undetermined coefficients. Okay, in this TR theta phi coordinates, we have spherical symmetry plus freedom to do general coordinate transformations has reduced our work enormously, and now we have only 2 undetermined coefficients, metric coefficients. Okay. So before that, some of you might be wondering why I put that minus sign, because I want to remember that T is timeline. So A is positive. Okay, A is positive, and B is space-like, so B is also positive. Minus A, so that makes dt the direction of time, and dr the direction of space. So these are positive, and this is A and B are both positive. So whenever we have a quantity which is positive, I can write it in the exponential form. That is, A is exponential of some real function, tr, little a, and B is exponential of some real function, little b, which is a function of t and r. Okay, because the reason is that the exponential function is always positive from 0 to infinity. If you or minus infinity to infinity in the entire range, the exponential function is always positive, definitely. Well, not definite, but okay. So if I write in this exponential parameterization, the same metric will now read something like this, with big A replaced by e to the little a, big B replaced by e to the little b, and we have to determine this little a and little b. Okay, so that is our next graph.